So this is a video on heaps. Heaps are kind of like a priority queue and binary tree mixed together. The way heaps work is that when you grab a value from the heap, you are going to get the value that has the highest priority. And in this example, I'm just going to use the priority as just the value. Other implementations, you can actually have a key, and you can have it evaluate the priority from the key rather than the value. But in this case, let's actually just look at values. So say I want to add some values here. I'm just going to put some random values here. All right, so if I want to add this to my heap, the way heaps work is that we want to make sure that the highest priority remains at the heap at the top, right, the top of the heap. So we do that by using reheapification. And basically, what reheapification does is it will keep moving a node to the top of the heap if it's not if it's larger than its parent, right? So let's say I have a yeah. Let's actually just implement this tree that we have here. So the first thing I do is I put in 13, so that's going to be the root. Then the next thing I do is put in 50. And notice I just put these in order. I don't have to worry about checking if the value is greater than the parent or less than the parent. We just put it in order. So that means root, left, right. Then once I put in the 50, then I evaluate this. I do the rehipification process. And I check to see if the entry that I just put in is greater than its parent. And in this case, it is. And so if it's greater than its parent, then all we do is we swap it with the parent. So now I put in 50 here, and now this is 13. All right, and so the next thing we do is put in 62. All right, and so 62, I do my rehipification. I want to see if the entry I just put in is greater than the parent. And in this case, it is. So I'm going to go ahead and swap it. So now I have 62 here, and I have 50 here. All right, the next thing I'm going to put in is 31. And remember, we just put it in order. So 31 will go here. And then I want to check to see if it is greater than the parent. And in this case, it is. So I'm going to swap 31 and 13. Then I want to keep checking. Is 31 now greater than its parent? It is not, so 31 will stay here. All right, the next thing I do is put in 29. Is 29 greater than its parent? It's not, so I'm good. Then I put in 5. And then I put in 2. All right, and so there is our heap. And one thing about heaps is that they will always be complete trees. And that is because we always put them in order. So it will always be it would always have if it has a leaf node, if it's not a full tree, then at most the leftmost will be completed. So this means that it will always be a complete tree. Of course, this case right now, this is a full tree. But full trees are also complete trees. All right, so let's talk about removing removing from our priority. Excuse me, from our heap. As we can see, 62 is the highest, right? So of course, this is what we're gonna remove, right? So we're gonna remove we're gonna remove 62 from our tree. So the way we do that is we're gonna first we're gonna copy our our value at the top. So we're gonna copy what was being removed, and then we're gonna copy the last entry in the deepest root, right? So the last entry is going to be 2, right? Because this is the last thing that we put inside of our heap. So we're gonna copy that as well. And then we're gonna go ahead and swap this value, right? So we're gonna now go ahead and put 2 here, and we're gonna get rid of this 2. And now we want to do our reheapification process, right? We want to get 2. We want to get the highest entry in our inside our heap to the top, right? So first thing we're gonna do is we're gonna check is 5 less than greater than 50. It's not. Now we say is 50 greater than 2. It is. So we swap our 50 with the 2. And then we check to see if the 31 is greater. And I'm sorry, I said we check the 5, but we don't need to check the 5 because we already knew that that the 5 was in the right place. So we would still want to check the 31 to see, make sure that the 31 is not greater than the top of the heap. And at this case, it's not. So now our heap is still in place, and we have 50 as the next. So let's go ahead and try that again. So now if I want to pop the 50, then I'm going to find the last thing that was in there. So this time it's going to be 5. So I'm going to swap 50 with 5. Of course, I'm going to remove the 5 from my tree. Excuse me. And then I want to do the reheapification. I want to see if any of the values are larger. And in this case, it looks like 31 is larger than 5. So we're going to swap 31 and 5. And then I want to check again if any of these are larger. And of course, I check with my 13. And 13 is larger than 5. So we're going to swap 13 and 5. And then I want to check the other child. And 29 is larger than 13. So we will swap 29 and 13. All right, and so now that we do that, we have reheapified our tree. And of course, the next highest value is still at the top, which is 31. All right, so that is removing from a tree. So now, how do we implement this? Implementation is pretty trivial with an array. When you do an array-based implementation, when you do a linked list, it is a little bit more difficult. So we're just gonna go ahead and do just the array for this assignment. So we're only gonna do the array implementation. You don't have to worry about doing the linked list version. I do challenge you, if you want to do the linked list version, I challenge you to do so, but I'm not going to make that a requirement. Your secret word is heap. And let's go ahead and talk about how we will do our swap. So as you know, with the array, when we do an array-based tree, our our node represents I. So if we have int I, this represents the index of the root, or should I say parent. All right, and then if we do left, the left child is going to equal 2 times I plus 1, and then the right represents 2 times I plus 2. All right, so that's how we represent our trees in the array when we do an array implementation. So if we are going to do our reheapification, a lot of times we just call it heapify. So let's say we have a function called heapify. And of course, whenever we do any type of examples, we are assuming that we're doing this with a we assume that we're doing this in a class. So just assume this in a class. And so we are going to need to start off with I, which is, of course, I said this is the root. And basically what we want to do is we're going to see if we're going to go ahead and create our left and right variables based off of I. So we want to actually make a copy of our I. So I'm just gonna call this int. I'm gonna call it top. Right, so that means that's the top of the tree. That's the highest. So we're gonna say that's equal to I. All right, and then we're gonna say int left is equal to 2I plus 1, and int right is equal to 2I plus 2. All right, and so now we want to see is the left child larger than the root, right, which is I. So we say if left is less than our size, right? So we got to think about the size of our array. So this size is going to be a member variable inside of our class, right? So we're going to say if it's less than the size, and then we also want to say and our array that we're using inside of our class at left if that is greater than the top, right, the top of our heap, then we are going to now make top equal to left, right? So that is doing a swap for us. Well, sorry, it's not doing a swap. It's just pretty much putting our left to we're recording where what should be at the top. So then, of course, we want to check to see if the right is greater. So we'll say if right is less than size, of course, and our array at right is greater than our array at the value of top, then we are gonna go ahead and make top equal to whatever the right is. Right, so notice it checks left first, and if it's set, and then if left is greater than top, it just makes the top be whatever the left was, and then we're gonna check again. So notice there's no else if. We're gonna check again. So left is now the highest, and then we just check to see is right even higher than what left was, right? And if it was, then we go ahead and make the top whatever right is. All right, so if none of those actually pan out, then we want to see, you know, if the top is actually not equal to, you know, our original parent that we sent in, then we're gonna go ahead and we're gonna do a swap, right? So this is just our regular swap function. So we just swap the value at I with the value at top, right? This is the new top that we discovered, right? And so we do that, and then of course this is gonna be a recursive call, right? We want to keep doing this until we don't get inside of this particular case. This is our stopping case pretty much. So we're gonna go ahead and say heapify. All right, and then we're gonna go ahead and send in, we're gonna send in top. All right, and so that will be our recursive function to reheapify our heap. All right, and so that's pretty much a heap. Pretty simple data structure, pretty easy to understand, very easy to implement inside of when we're doing an array, a little more difficult when you're doing a linked list. Again, I challenge you to do the linked list implementation. Yes, as far as inserting into an array base, it's going to basically be the same thing. We don't have to check to see if left is less than parent or right is greater than parent. All we do is we just put in our node in the next place that it belongs, right? So if I have a node here, I just put it in the next place here, and then I reheapify. Then the next time I put it in here, then I heapify. Then the next time I put it here, and then I heapify. And so that's the way heaps work, and that will guarantee that the very top node is always the highest priority. All right, thank you for watching.